Today we summarize the results of Poisson distribution. That is, X follows Poisson distribution with the parameter lambda implies f of x equal to e raised to minus lambda raised to x by x factorial x equal to 0, 1, 2, etc. up to infinity, lambda greater than 0. Lambda is called the parameter of the distribution. Okay, lambda is the parameter of Poisson distribution. Then for Poisson distribution with the parameter lambda, mean equal to variance equal to lambda, mean equal to variance for Poisson distribution equal to lambda, and standard deviation equal to root of variance equal to root lambda. Okay. Then the moment generating function of x's mtx equal to e raised to lambda into e raised to t minus 1, e raised to lambda into e raised to t minus 1. We can find the mean and variance using the MGF, that is mu1 dash equal to d by dt of mtx at t equal to 0 gives mean equal to lambda, and mu2 dash equal to d square by dt square of mtx at t equal to 0 gives lambda square plus lambda, and hence mu2 equal to mu2 dash minus mu1 dash square gives variance also equal to lambda. There are two methods. There are more than one method for estimating the moments. Okay. We can also find the mean and variance using the MGF. Now the additive property of Poisson distribution, that is, if x follows Poisson lambda 1, y follows Poisson lambda 2, x and y are independent, implies x plus y follows Poisson distribution with parameter lambda 1 plus lambda 2, the additive property of Poisson distribution. Okay. Now we have the recurrence relation for the raw moments of Poisson distribution as mu r plus 1 dash equal to lambda into mu r dash plus d by d lambda of mu r dash, lambda into mu r dash plus d by d lambda of mu r dash. So that we have, if we have mu r dash, we can obtain mu r plus 1 dash. Mu naught dash is 1, which is expectation of x raised to 0. Mu 1 dash equal to lambda, which is the mean. Mu 2 dash equal to the second row moment equal to lambda square plus lambda. Mu 3 dash equal to lambda cube plus 3 lambda square plus lambda. Mu 4 dash equal to lambda raised to 4 plus 6 lambda cube plus 7 lambda square plus lambda. Okay. The 4 raw moments of Poisson distribution. Now, the central moments of Poisson distribution can be obtained using the relation between the row and central moments. Otherwise, we have the recurrence relation for the central moments as mu r plus 1 equal to lambda into r mu r minus 1 plus d by d lambda of mu r. So that if we have mu r, we can obtain mu r plus 1 using this relation. We have mu naught equal to 1, mu 1 equal to 0 for any distribution. Okay, then for Poisson, mu 2 equal to lambda, mu 3 equal to lambda, mu 4 equal to 3 lambda square plus lambda. Okay, now beta 1, the measure of skewness is mu 3 square by mu 2 cube. So for Poisson, equal to 1 by lambda, which is greater than 0, as lambda is greater than 0. That is, what about Poisson distribution? It is positively skewed. Okay. Now beta 2, it is the measure of kurtosis equal to mu 4 by mu 2 square. So on substitution we get it is equal to 3 plus 1 by lambda. So that greater than 3 for Poisson distribution, that is Poisson distribution is leptokurtic. Poisson distribution is leptokurtic. Now we have the mode of Poisson distribution. We know mode of a distribution is that value of x for which f of x is maximum. Okay. So if x is the mode of Poisson distribution, we have lambda minus 1 less than or equal to x less than or equal to lambda. Already we have proved this result. Then there are two cases. If lambda is not an integer, then Poisson distribution has a unique mode given by the integer part of lambda. If lambda is an integer, then Poisson distribution has two modes given by lambda minus 1 and lambda. Now we have the conditional distribution. The result is if x follows Poisson distribution with parameter lambda 1, y follows Poisson with parameter lambda 2, and x and y are independent random variables, then the conditional distribution of x given x plus y is binomial. Okay. Now we consider the recurrence relation of probabilities. We have f of x plus 1 equal to lambda by x plus 1 into f of x. This result is useful in fitting of Poisson distribution. Now, what is meant by fitting of Poisson distribution? Suppose we have given a frequency, distribution for which x takes value 0, 1, etc. to n. Okay. And the frequencies are f0, f1, f2, etc. fn, such that sigma fi equal to capital N, the total frequency. Now, fitting of Poisson distribution is the process of estimation of the parameter lambda of Poisson distribution using the given data and obtaining the theoretical frequencies using the Poisson distribution for the given data. Okay. So that we assume x follows Poisson lambda, and hence f of x equal to e raised to minus lambda, lambda raised to x by x factorial. X has values 0, 1, etc. to n. The parameter lambda is estimated by equating the mean of Poisson distribution with that of the given frequency distribution. Thus we get lambda estimate as equal to x bar. Okay, equal to, so 1 by capital N sigma x into f, divided by capital N. Now using this f of x, we can obtain f of 0 as equal to e raised to minus lambda. Then f of 1, f of 2, the probabilities are obtained using the recurrence relation. That is, by putting x equal to 0, we get f of 1 as equal to lambda by 1 into f of 0. X equal to 1, we get f of 2 as equal to lambda by 2 into f of 1, etc. And finally, expected frequency EI equal to capital N into f of x. We have to check, we have to confirm the total sigma EI equal to capital N. Okay, and we can form it as in the form of a table, which is the expected frequency table. Okay. Now let us compare binomial distribution and Poisson distribution. Okay. As in the case of binomial distribution, it was discovered by James Bernoulli. Hence, we call point binomial distribution as Bernoulli distribution. Whereas, Poisson distribution was discovered by Simeon Dennis Poisson. Hence the name Poisson distribution. X is in the case of binomial distribution, X is the number of successes in a definite number of independent trials. For a finite number of trials, X is the number of successes. Whereas in the Poisson process, X is the number of successes in a sufficiently large number of trials. Poisson distribution is applied when n tends to infinity, p tends to 0, probability of a success being very small, and hence np equal to lambda should be finite. It is called the law of improbable events as it is applied in the case of rare events. Okay, the number of successes is so small. Now, binomial distribution is applied in quality control, whereas Poisson distribution is applied in queuing theory, in insurance, etc. Then, binomial distribution is, for binomial distribution, mean is greater than variance. Mean is greater than variance for binomial distribution. Whereas for Poisson distribution, we know mean equal to variance. For Poisson distribution, mean equal to variance. Okay. Now, binomial distribution is symmetric if P equal to Q equal to 1 by 2. It is positively skewed if P less than 1 by 2 and negatively skewed if P greater than 1 by 2. Whereas Poisson distribution is positively skewed and leptokurtic always. Okay. Now, binomial distribution tends to normal distribution as n tends to infinity, whereas Poisson distribution tends to normal distribution as the parameter lambda tends to infinity. Both tends to, binomial and Poisson, both tends to normal distribution. Okay, thank you. We conclude Poisson distribution.